Okay, we'll continue with Yao Wang from Emory University.
Yeah, thanks for your introduction, and I want to thank the organizers for putting together such a great meeting. Especially we have a separate session about entanglement witness, and yeah, thanks for inviting me here. I will use this screen. I will talk about, continue with the first two accident talks. I want to dive into entanglement witness, but I will talk about indistinguishable particles, indistinguishable fermionic particles using X-ray spectroscopy. So let me briefly recap of what all the previous two talks has mentioned. When we talk about the entanglement, we always define a separable state as a tensor product of two partitions, and the entangled state means we cannot find such a way to partition the function into two parts. So this is how we usually, there's no debate on how we define entanglement. And there are various applications of entanglement. That's what I want to make a disclaimer here. We can use this type of entanglement to discuss quantum information, quantum communication, teleportation. So you only need the entanglement of two particles to talk about teleportation. We can use entanglement to classify the long-range entanglement in topological entanglement, the exotic topological order, like fractional quantum Hall state. There is another type of application of quantum entanglement, which is, we can talk about multi-party entanglement in many-body systems, which characterize the complexity, intrinsic complexity of the system. I think we have a lot of audience working on quantum simulation, quantum computing. This is also related to quantum simulation, basically classifying what's the intrinsic number of qubits you need to use to simulate a material system. For example, if we talk about a Fermi liquid, you only need basically 1 qubit to describe non-interacting electrons. So this is what I want to start with, the multi-party entanglement. And I do not want to dive into the other two topics, like topological entanglement and teleportation. These are also interesting topics that we can also spend an hour talking about each of them. But I want to only focus on the complexity of the many-body system. So just to give a cartoonish picture, if you have a many-body system, or instead of just a two-particle, we always know how to define entanglement. If we have a many-body system, the separable state is still the product of all individual single-particle states. And when we talk about entanglement, there are different hierarchies of the entanglement. You can have the entangled wave function constitute of only a few blocks of the pair spin states. That's called the bipartite state. But you can also have some situation where you have a larger partition where they cannot be separated. You can have a tripartite or four-partite state. So they indicate different Hilbert space dimension if we talk about quantum simulation. So that includes it means you have to use more qubits. Intrinsically, you cannot reduce the number of qubits to simulate these systems. So to distinguish them, we usually call them bipartite, tripartite, or k-partite state, depending on the maximum particles that cannot be separated. So I usually represent this state using this figure. You have the separable state, bipartite, tripartite, four-partite, and keep going. Actually, the higher you go, the larger Hilbert space you have, the higher dimension you have for many-body states. And just to make sure we are on the same page of the terms, we usually call a separable state and bipartite together as a so-called two producible state, meaning it's at most a two particle that can be, two qubits can describe the system. And altogether with up to tripartite state is called three producible states. And similarly, we can define k producible state as a container of all the k and k-1, k-2 until separable states. Okay, so using this definition, I think this has been heavily studied in cold atom systems. I want to mention an experiment done by Marcus Grana 10 years ago. Well, we all know that the entanglement can be measured by the purity of the state when you trace off part of the system. So by tracing off a separable state, a pure state becomes a pure state. Nothing will really change. But if you trace out a mixed state, a entangled state, you will get a mixed state, and that's how we get entanglement entropy. And the partition of the system becomes more mixed when you try to trace off the other partition. So using this idea, Marcus designed a very important cold atom system using the twin state interferometry, preparing two identical many-body states, and use the interferometry to, well, you collapse them and to count the number of particles on each side of each partition of the system. And in this, this is actually a bosonic system, but there is a many-body statistic that if you have a pure state, then the partition has to have the even number of particles. If you have the odd number of particles, that means they have you enter the mixed state. And using this idea, they can classify the multipartite entanglement. So this is already well investigated 10 years ago in cold atom system. And well, in terms of quantum information, cold atom is always far beyond what solid state can do. But if we try to apply this idea into solid state, we will have the following problem. Well, in materials, we do not have identical wave function. You cannot prepare twin state. You cannot call this material identical to the other. And you have limited correlation function. You cannot access so many multi-point correlation functions, and all the spectral measurement has limited resolution. So that's why we have to design a compromise to measure multipartite entanglement. That's how the entanglement weightedness idea come from. As Alan mentioned in the first few pages of the talk, well, the original idea of entanglement weightedness come from the Bell's inequality. So if you have, I use a special form of the Bell's inequality. Well, if there are some inequality that you have to satisfy if your state is classical, and once you violate this, this is an indication of the entanglement. But well, this is just to test whether you have entanglement or not, but it doesn't tell you whether you have bipartite, tripartite, or multipartite entanglement. So the idea is extended to a general violation of inequality if we talk about a multipartite entanglement. If we have the following figure, the following hierarchy of the entanglement, we can always find some operator O, and for a K-producible state, this is a finite set, a finite dimensional set of states. For K-producible state, if this O operator's expectation value is bounded by some maximum number and minimal number, we call it O max and O min, well, as a function of K, if these maximum or minimal bounds are monotonic with the K, with the K-producible state, the entanglement depth K, and O is measurable in solid state, then we can call this O a very nice entanglement weightedness, because this can be used to classify in which class you finally end up with in this hierarchy of the entanglement weightedness, entanglement depth. So I draw some contour of this O operator's upper and lower bound. So this minimal and maximum O value doesn't have to be consistent with the boundary, the exact boundary between different class of states, different entanglement depths, but it can be used as good approximation and always a lower bound of the entanglement depths. So yeah, as the previous two talks already mentioned, the quantum Fisher information is a very important, very useful tool for the entanglement weightedness. It's almost the equivalent to entanglement weightedness in the past few years. So the idea is if you have a K-producible state and you measure the quantum Fisher information, which is the characterization of the quantum fluctuations of the spin system, you can easily characterize using the inequality of the FQ always smaller than 4K times S squared. K is the entanglement depth. you can always characterize the lower bound of your entanglement depth K. So this is this is popular because quantum feature information is found to be measurable by spin spectrum, dynamical spin structure factor, which is accessible by neutron scattering. So this was shown by Philip Hawke and Peter Zoller almost 10 years ago. And I showed the first paper published by Alan Shea in 4 years ago. So I actually was motivated by this paper when entering this field. So this is the first experimental realization showing that, okay, the quantum feature information is indeed measurable by neutron scattering. You can get precisely the value of feature information compared to the DMRG simulations. So Alan and Yuan have talked a lot about the quantum feature information. This is not the main part of my talk. What I want to really discuss is how do we move from the characterization of the spin entanglement to a general indistinguishable particle, many particle system. So for a spin system, a quantum feature information is a natural definition of a natural characterization of entanglement because a spin system has its natural basis. Right? You talk about local spin and you know what you talk about for a local spin mode. So you can use this definition of entanglement depth being the maximum number of modes in this tensor product form, and you've just defined count the number of spin. There's no ambiguity of the spin system. Of course, there is a real space momentum space thing, which is I think Alan already discussed a lot about this. But for indistinguishable particle, for electronic system, or even for bosonic system, there is some ambiguity. First, if you think about fermion systems, you cannot really write anything as a product state. There's no such a product state if you talk about indistinguishable particle. We all know that there is anti-symmetry for neutral exchange. So even for two fermion state, the wave function, non-interacting wave function cannot be written as a tensor product. You have to write something like this, right? The stator determinant form. And for n particle state, it's more complicated. You have to write, even for non-interacting system, the stator determinant has n factorial number of terms. So if you just apply quantum feature information to this form, you will find, okay, even for a non-interacting Fermi gas, you have infinite number of entanglement in the thermodynamic limit. So you are comparing infinity to infinity now. So according to, this is not what I propose. This has been discussed like 20 years ago when we tried to distinguish entanglement to categorize entanglement in indistinguishable particles. You should avoid taking into account all these the fermionic exchange function. So while this has been solved, of course, during the past 2 decades, instead of using wave function as the tensor product, you can use the creation operator because all these exchange operations have been already taken into account in the fermion creation operators algebra. So you can write redefine the entanglement depth by how you can partate the creation operator as a creation operator in an irreducible partition. So if the wave function can be written as a product of the creation operator in all these m partitions, and for each partition it's no longer reducible, this is how we can redefine the entanglement depth following the way we did for qubits or for spin systems. Of course, that's not the end of the story because you can easily recognize for different from the spin system, for fermion, we do not have a natural basis. We always use the basis we artificially define when we talk about, for example, the s orbital, p orbital. Well, these are just the artificial wave function basis we use to project the system. And for example, if we talk about a Fermi C, non-interacting Fermi C, it is, of course, infinitely entangled if we use the real space basis to describe it. But well, for those working on quantum simulation, quantum computing, we all know that this is just we didn't choose the best basis to describe the system. You can just rotate the basis into the Fourier basis, the momentum space, then this becomes just a product state. So the question comes here that we have the ambiguity of the basis for fermionic system, and we may reduce the entanglement depth
by just changing the single particle basis. And by finding the correct, the optimal single particle basis, we get the minimal value of entanglement depth, which is more efficient for quantum simulation, quantum computing of the same many-body system. So that means if we want to find some definition of the entanglement depth that is invariant under the single particle transformation, unitary transformation of the basis, which is something, oh, sorry, there's an animation issue, which is something that can be described by the Gaussian transformation. If you have a e to the c dagger c Gaussian transformation, that's equivalent to a basis rotation of a single particle fermionic basis. So the idea is if we convert this maximum partition problem into a minimax problem for all the possible Gaussian transformation, we find the minimal entanglement depth of the defined basis problem. This is the intrinsic irreducible entanglement depth of the fermionic system. And another little bit trivial thing, a minor thing, is that, well, we do not have a well-defined fitting for fermionic system. Even for a single atom, you have infinite number of bases. So when we talk about fitting, we talk about something in our, again, in our human's mind, we have a truncation of the basis. So we should talk about particle instead of orbitals. So instead of talking about orbital, we talk about the minimax of the particle. So using this notion, we can define our entanglement weightness for fermionic system. So the idea is, if we have a entanglement weightness that works for indistinguishable particles, we have to satisfy the following conditions. It has to be resilient to the intrinsic fermionic antisymmetry. You cannot just call the antisymmetry the part of the entanglement. And you can you have to define something invariant under the unitary basis transformation, which means you always capture the intrinsic entanglement depth instead of the one induced by the choice of basis. And another thing which is intrinsic for the entanglement depth is you have to be monotonic to the entanglement depth. So you have to make sure that your quantity is proportional to, or is at least monotonic to the entanglement depth k. And the last thing is that it has to be measurable by spectroscopy, by something realizable in solid states. So in the remaining of the talk, I will show you that we found a quantity that satisfies these four conditions, and we can use it to quantify the entanglement depth of the indistinguishable fermions. So the quantity we used is the so-called two-particle reduced density matrix. It's not the quantum information language of the reduced density matrix. It's one of the chemistry language. Is the c dagger c operator. Well, you can think about if we have the I equal to k and j equal to L for the first fermion operator, you get the spin-spin correlation or charge-charge correlation. That's that reduced to our QFI, quantum Fisher information. Right? But we use a completely four fermion tensor form of it. And similar to what QFI did, we also subtract off the classical components of the 2RDM. This becomes the so-called two-particle cumulant RDM, 2C RDM. So which means you have all the weak theorem, weak expansion of the lower order terms, and you only calculate the connected part of the four fermion interaction, fermion correlation. So that ensures that this entire operator vanishes for a stator determinant in the Fermi C. So that can protect us from, well, something diverging in the just because of the Fermi statistics. Another important property for this tensor is that when you have the basis transformation, which is well, we rotate the C operator by a unitary matrix U. Well, this RDM will not preserve, but it will rotate in the same way. It will rotate also in the unitary transformation. So that indicates that something intrinsic that will be invariant under the rotation, which is the singular value of this tensor. Right? So if the singular value of this tensor serves as the of the purpose of invariance for unitary transformation. Right? So well, we calculated the tensor singular value, but in the remaining of the talk, I will use the simplified version, which is you can flatten the tensor into a matrix by grouping IK and the JL indices and calculating the eigenvalue of the flattened matrix because this is easier to calculate. Okay, so using this notion of the defined partition and entanglement depth, we can easily show that our goal can be achieved by simplify the problem into a few individual separated problems. We want to find a maximum upper bound for the OOP for the 2C RDM, which satisfy that this maximum value is monotonic with the K producible state with this K. So because of this notion of the separable, the C operators, you can find that the maximum eigenvalue of this tensor is actually the maximum of all among all different partitions. You only have to calculate individual partition because the different partitions do not mix in this notation. You can easily verify. So this is basically a block diagonal matrix. So you only have to calculate the upper bound, the supreme, for the eigenvalues of each small partition. You do not have to talk about the all the thermodynamic system. So that makes our life easier because we can traverse all possible states of an n-producible partition. For example, for a 2-producible state, you can write all wave functions, all 2-producible wave functions in the following form, that the sum over ij, the wij ci dagger cj dagger acting on the vacuum, and this omega ij operator is anti-symmetric. So this is a quantity that has been studied in 20 years ago by the quantum information theorists. It can be decomposed by so-called Setter rank, Setter decomposition. You can easily find the upper bound of this eigenvalue. This mu for 2-producible state is 3/4. You can prove it rigorously. And for I do not want to show you the proof. I only want to show you the numerical results that you can easily visualize. We actually sampled 1,500 samples of this coefficient. You can see this is for half-field system for 2 electrons in a 4 orbital. You have all this distribution of the eigenvalues, and it's capped by 3/4. This capped state is actually nothing but the 2-particle GHZ state. And if you dope it, you only make this number smaller, but you still occasionally reach the upper bound. That's because of the ambiguity of the definition of fading. Because if you even have a field system, you can only cluster all your electron to a part of the system and make it highly entangled and leaving the remaining side completely empty. So that means this, this is actually mathematically accurate. I just want to show you the numerical evidence why this is true. We can also push to the 3-producible state, which is become the 3 tensor of the coefficient. This is no longer mathematically exact, but we actually we calculated using a subclass of this problem, the GCD-like generalized GHZ state in the 3-producible state, and show the upper bound is 5/4. And we verified this by numerically sampling all the states. I only show the small class of sampling, still 1,500 states. You can see that still you have the sampled state bounded, the eigenvalue of the sample state bounded by 5/4, and this upper bound is nothing but your 3-particle GHZ state. Of course, if you keep doping, you will get the average value lower and lower. So we can further push our proof and our numerical calculation to K-producible state, and you can find that for K-producible state, you get half times K minus a half. So this result actually was observed, was concluded by David Mazzalti actually a year before we published the paper from a different perspective. Also for slightly different condition. So in the end, we show that for a K-producible state, this upper bound for the 2C RDM's eigenvalue is proportional, is a monotonic with the entanglement depth K. So this is good because this is the third condition we need for entanglement witness. We need the observable to be monotonic with entanglement depth k. So the last point is we have to make sure this is something that can be measured in solid state spectroscopy. Otherwise, we are talking about something that we cannot really realize. So that comes to the another concept, which is inelastic X-ray scattering. That's a field I have been studying for a decade. The resonant inelastic X-ray scattering. This is usually regarded as a substitution for neutron scattering in the X-ray beam line. So the key idea is you have the X-ray incident, you have the incident X-ray photon, and can kick out a core level electron into the valence band, which create a n+1 electron in the valence system. And this intermediate state has a finite lifetime because the core level carries a huge energy. So after some finite lifetime, you will have the emission of the electron back to the core level. You have the recombination of the particle hole, which emits a scattering X-ray photon. And this emission will leave the system with a particle hole excitation in the valence. And that causes the excitation. Of course, if you think about the lifetime to be infinitely short, if you shorten it, ultimately you will collapse this emission and the absorption process, and you just create a particle hole that's similar to the neutron scattering. So you get nothing but a charge or spin operator, depending on whether you flip the spin for this particle hole. That's usually the approximation we use when we describe the X-ray scattering, and we try to describe the spin spectrum. And we also have some papers using this Riggs spectrum to identify quantum Fisher information for spin entanglement. But what's important is that Riggs is not really ultra short lifetime. We actually have something more than that. If we just use the ultra short cohort lifetime, we get local operators, we get local spin or charge operators. That's quantum Fisher information. But if we consider the intermediate steps, we actually have much more than that. The intermediate step has a finite lifetime. This gamma is a finite value; it's not infinite. So you have the intermediate state propagating for a finite duration before the second photon enters, before you emit the X-ray photon. So this process is usually described by the so-called Kramers-Hasmer formula. You have the two propagators in the formula, actually three, because you have the left and right vector. So in abbreviation, you can think about this excitation as not only the local excitation, but also there are also other longer, higher order fermionic excitation in the end in the system. You have the C dagger C, C dagger C, C dagger C, and the infinite orders. So this gives us something that we can leverage, because in RDM, we really want to measure this C dagger C operator. And we want, if we can extract this information from Riggs spectrum, that means we have a way to measure the 2C RDM. So the question is, how can we extract this high order term? Oh, this is actually not the leading term compared to the spin and charge. How can we extract this from X-ray spectrum? So there is actually something interesting in the X-ray spectrum. If we consider the holes, the intermediate state has a core level hole, and this core level hole is not just static there, because the core level has this bandwidth. If we consider the core level hole to be mobile, then this incident particle hole pair will be at a different location from the emission particle hole pair, because this core level, or the H prime, which is the intermediate Hamiltonian, has a local part of the Hamiltonian and the core level kinetic energy. So you have a probability to move the core level to a nearest neighbor site, and that can give you a particle hole excitation for the nearest neighbors, the CM dagger, CM+1. So, well, this is just the conceptual perturbation process, but this can be, well, as long as this process can be realized, can be measured, you get the C dagger C operator from the fermionic, full fermion part. Well, we can do a perturbative expansion of this process by the core level kinetic energy T. So the zeroth order expansion is still our local Riggs excitation, and you have the T's first order, second order term, and keep going. Well, And again, this is just a conceptual theoretical expansion, and experimentally you cannot do perturbative theory. There has to be something different for the first, something can distinguish the first order from second order, from the zeroth order to do the experimental measurement. So what we found is if we substitute the first order, second order into our Kramers-Hessinger expansion, you will get different momentum dependence terms. For the first order, second order of the cross section, you get the incident energy and scattering, incident momentum and scattering momentum dependence. But for the zeroth order term, which is usually what we discuss in the Rig spectrum, your spectrum only depends on the momentum difference between the incident and scattering momentum. So using this defining feature of this first and second order spectrum, you can define a momentum filter that can filter out the first order and second order term, which will directly lead to the full fermion term. So I will skip all the derivation, but I just want to show you that if we have some momentum field design some momentum filter, you can completely zero out the zeroth order term and get the information from the first order, second order. And of course, this is, well, if I just tell you like this, you won't believe me. I will have to show you the numerical simulation. This is a numerical simulation for rigs using a Hubbard model ED calculation. Well, you can see that for when we have a core level kinetic energy, for fixed energy transfer, you will get the incident momentum dependence. Fixed momentum transfer, you will have the slightly difference for different incident momentum. That's already an indication that, well, our assumption of the immobile hole doesn't hold anymore. So using the momentum filtering, you will get the 4-point correlation function like this. So the dark blue bar, they are all these 4-particle correlation functions calculated from the ground state wave function. And the light blue bars are those extracted from Rig spectrum. Of course, our calculation has the numerical error. You have the finite energy window. You have some error bar, but you almost reproduce all these 4-particle correlation function. So the upper panel is a spin conserved, and lower panel is a spin flipped correlation function. So the take-home message is you can use some momentum energy filter of the spin of the Rig spectrum to get these 4-particle elements. And so how many minutes I have?
You're past the 30 minutes of speaking.
Oh, sorry. So let me flip. So I only want to show you that this can be measured by solid state spectroscopy. And here I use some many-body models to show that, to demonstrate this. So I will move fast. For the lower panel, I showed QFI for a doped extended Hubbard model, and for the upper panel, I showed the eigenvalue from RDM. You can see that for a doped system, because it's no longer magnetic ordered, the QFI will no longer will be inefficient to characterize the entanglement depth. You will not get the witness entanglement, but for RDM, you still get the entanglement. And also for the spin liquid, you can also do the same thing. When you have the spin dominant quantum spin liquid case or the dimer order, you have spin orders system. What result you get from the QFI in the lower panel is consistent with what you get from the RDM, because apparently for a spin order system, RDM becomes QFI. But when you lower this U to almost a non-interacting limit, you will get a metallic system, and the QFI no longer works to characterize the entanglement, but the RDM can still characterize the entanglement between electrons. Okay, I will skip. I actually prepared a slide for quantum geometry, but I will skip this and go to the summary. I will basically discuss the notion of multi-particle entanglement among indistinguishable particles, indistinguishable electrons, especially how to characterize using X-ray spectrum. I want to thank my students, postdocs, and the collaborators for this project.
For 1 or 2 burning short comments. Yeah.
Thank you. This is really fascinating. I'm curious about the numerical results you showed at the very beginning, where the RDM seems to be increased by the filling away from 1/2. Seemingly, as you make the electrons more dilute in the system, this makes it harder and harder to meet. Have you explored whether there's a rigorous bound for this, that the electron density is relation to entanglement?
Yeah, very important question. Yes, we actually have a analytical bound for each individual doping with well, it's quite a few slides away, and let me just move it. Yeah, so for different doping, we can actually get a different bound, and for a doped system, we actually get a analytical upper bound if this is homogeneously doped. But if you just sample the state, you will find there are occasionally some states that you actually, well, the doped system is undoped system is a subset of doped system. You can cluster all the doping to a few sites and make the remaining undoped. So in the end, you have occasional case that you can pass the bound. But if you force the system to be homogeneous, you will have a, well, this is like 1/r decay. It's a longer formula than 1/r, but it's one constant term plus 1/r. So it's a decaying term for homogeneously doped system.
First of all, spending for not ultra short evolution lifetime. You mentioned tunneling support. Usually there's a focal potential which is much larger.
Right. It is also included. It's included.
Well, and still get the same analysis. No, actually don't know what's
Right. So this is also an important point that the core potential is a very strong interaction. It's non-perturbative. You cannot just perturbatively expand the core levels. We have to explicitly include it in the ED calculation. And yeah, we tested all these different core potential. This doesn't affect the way that we perturbatively expand the core kinetic energy, but this will affect the spectral spread of the entire energy window. So if we just fix the energy window and calculate the multi-particle the correlation function, well, that will introduce some numerical error because of the core potential. But this is not an intrinsic thing in the calculation.
So let's thank Yao once more.